Hi everyone. In this chapter, we're going to be focusing on applications of integrals, so really getting more into kind of AP topics around integration. So for today, we're going to start talking about accumulation functions, and in a little bit, we'll get to exactly what those are, but we're going to start off by reviewing the fundamental theorem that we worked with in the last chapter. Now, I do have to warn you, this is likely going to be a long video, but hang with me. All right, so to review, we're going to find f prime of x for the following functions. Now, here we have a function that's defined as an integral. And so to find f prime of x, we're going to take the derivative with respect to x of our integral. And so hopefully when we see this, we should all realize this is just our fundamental theorem here. Right? The idea being that differentiating and integrating are inverse processes. So as long as my lower limit is constant, here my upper limit is just x, so it makes it a nice and easy problem. I'm just going to substitute x for my variable, and my derivative is x cubed. Now the next one, same idea, still fundamental theorem. But now it's just a little more complex because I have an upper and a lower limit that are both functions of x. 3t squared dt. So now I'm going to plug this in still. So I'm going to get 3 times sine of x. I'm going to put that in parentheses because this t is squared, so my sine of x is going to be squared. But then remember, because this is a function of x, I need to multiply by the derivative. So I have times cosine of x. And then I subtract my lower limit here. So I'm going to plug x squared in for t. So I'm going to have minus 3 times x squared, quantity squared. And then I'm going to multiply by the derivative. So derivative of x squared is 2x. So if I have a little simplification here, let's see, we'll just make this 3 times cosine of x times sine squared of x minus, what do we have, 6, x to the 4th, x to the 5th. And that would be our derivative. So that's fundamental theorem, and that's actually going to come into play a lot as we talk about these accumulation functions. So the first thing we need to understand is exactly what an accumulation function is. Okay, and it's just any function which is of the form y equals the integral from a to x of f of t dt plus c. So if you think about it, even though we didn't call it this, you guys were writing these accumulation functions in the last chapter. Okay, and so really what they are is any function that's expressed as an integral. Okay, and so what we're going to be doing in these first couple days is analyzing these accumulation functions. Okay, and so there's a note here. When we study accumulation functions, we're often asked to analyze them using the same ideas we learned when analyzing functions using derivatives. And you'll see a lot how that comes into play in this first video. Now, the key here really is these aren't that hard, but you have to really pay attention to the detail because it's easy to get our functions mixed up. So you just need to go slow and be very careful about the functions that you're working with. So here we go. We have about, I think, 4 topics to cover in this video. So kind of basic ideas we need to be able to do with these accumulation functions. So the first one is to find a function value when we're given an accumulation function. So it says, suppose f is the function whose graph is given at the right. I highly recommend you labeling the graph of f, because otherwise it's very easy to get confused between what's g and what's f. So f is a function whose graph is given at the right, and g of x is given by this accumulation function. Now you can see my accumulation function references the function f. Okay, so we're going to use this accumulation function and my graph to find these values. So if I want to find g of 0, The biggest mistake people make is they go to the graph here and say, well, g of 0 is 0 because this point is here. But remember, this is the graph of f. So we have to be careful. G of 0 is really, we're going to use our integral here. The integral from 0, now our x is 0, of f of t dt. So it actually turns out that that value is going to be 0, but it's because this integral from 0 to 0, I haven't accumulated any area within that interval. So that's why the value is 0. Okay, so let's look at g of 4. Again, g of 4, I have to go back to g, is the integral from 0 to 4 of f of t dt. So now that's telling me, well, the integral from 0 to 4, we know that's just the area between the x-axis and our curve. So it's all of this area in here. So we have to use our geometry formulas. Okay, so let's see. I can do between 0 and 1. Actually, let's do this. It looks like I've got a trapezoid here. And then I'm going to have a quarter of a circle. So let's do our trapezoid. So the height of that trapezoid is 2. So 2 over 2. My base 1 is 1. My base 2 is 2. And then I have my quarter of a circle here. So plus, let's see, my radius is 2, so pi times 2 squared over 4. So if I simplify it, I'm going to get 2 plus 1 is 3, plus, that's going to cancel, 3 plus pi. Okay, so when I'm finding the function values of g, I'm just using the graph of f to evaluate those integrals. Because then again, this integral is just the area trapped between the curve and the x-axis over that interval. Okay, so that's finding function values from a graph. Now, for number 2, we're given a function here, a specific accumulation function, and we're asked to find the same thing. So, for g of 0, I'm going to have the integral from 1 to 0 of t squared minus 1 dt. So now I just have a definite integral. Now we're not using geometry formulas anymore. We're going to use our antiderivatives to calculate this definite integral. So again, since I have my limits of integration here, my answer should be a number. So my antiderivative is going to be t cubed over 3 minus t, and I'm integrating from 1 to 0. So if I evaluate at 0, I just get 0. Minus, now I'm going to have 1/3 minus 1. So let's see, 0 minus 1/3 minus 1 is a negative 2/3. So my value is positive 2/3. So g of 0 is going to be 2/3. Okay, let's do the same thing to find g of 2. Again, I'm going to go back to my function here. So g of 2 now is going to be the integral from 1 to 2 of t squared minus 1 dt. So same thing. I have a definite integral. I'm going to antidifferentiate and evaluate. So t cubed over 3 minus t from 1 to 2. So let's see. I'm going to get 8/3 minus 2 minus 1/3 minus 1. So let's see, 8/3, this is going to be 6/3, so I'm going to get 2/3 minus, this is going to be a negative 2/3. So my answer is 4/3. So that's the first thing we need to be able to do, is just find the function value if we're given an accumulation function. All right, moving along. All right, next we need to be able to find first and second first and second derivative values when we're given an accumulation function. So now you'll notice instead of just finding the value of g, we're looking for g prime and g double prime. So before I jump into specific values, I want to figure out, well, what's the function that defines g prime or g double prime? So I'm going to just use some workspace here. I know that g prime of x is the derivative with respect to x of my integral, 0 to x of f of t dt. Let's see if I can focus this a little better. It's a little blurry. Not much better. Okay, so g prime of x is the derivative with respect to x of my integral from 0 to x of f of t dt. Well, we should recognize, again, that's just fundamental theorem. So what this is telling me is that the derivative g prime of x is actually f of x. So this function that I'm given in the graph is actually the derivative of g of x. And so now, if I need to work with g double prime of x, I know that's just f prime of x. Okay, so let's go ahead and look at this then. G prime of 0. Well, I know that g prime of 0 is really just f of 0. So using my graph, f of 0 is going to give us 0. Okay, now g double prime of 2, we said g double prime of x is f prime of x, so it's f prime of 2. Now remember, what that's asking us is, what is the slope, right? If I want f prime of 2, it's asking me, what's the slope of f when x equals 2? So that's also going to give us 0. Okay, and I'm going to make a note of that actually. F prime of 2 is asking for the slope of f prime at x equals 2. And that's how we get 0. Okay. Let's look now if we're just given the function. Now we don't have a graph. Same idea applies though. So maybe I'll put this, let's see, over to the side here. Now I notice I need to know g prime and g double prime. So I'm just going to go back to my basic function. I know that g prime of x is equal to the derivative with respect to x of the integral from 1 to x of t squared minus 1 dt. Again, this is just our fundamental theorem. Taking the derivative of an integral, my lower limit is a constant, my upper limit is x, so I'm just going to substitute. G prime of x then is x squared minus 1. So now I know that g double prime of x then is just 2x. So if I'm very careful about doing that beforehand, then finding these values becomes very easy. So now g prime of 0, I just go back to g prime of x, is just 0 squared minus 1, or negative 1. Okay, over here, g double prime of 2, g double prime was 2x, so it's just 2 times 2, or 4. All right, so now that we know how to find some function values, how to determine derivative values, we can do some more complex work, and we're going to start talking about, well, how do we determine when an accumulation function is increasing or decreasing, or concave up or concave down? So these are all things we've done with our regular functions, and now we're going to be doing just the same thing with accumulation functions. All right, So here we have, it says f is the function whose graph is given at the right. So I'm going to put that so I don't get confused. I'm very clear that this is the function f. Okay, so this is the function whose graph is given at the right. And again, I have my accumulation function, g of x equals the integral from 0 to x of f of t dt. So I need to find the intervals where g of x is increasing and decreasing, and where I'm concave up and concave down. Well, I know for increasing and decreasing, right, that has to do with the first derivative. So I know that g of x is increasing when g prime of x is greater than 0, right? We know increasing is where the first derivative is positive. On the other hand, I know it's decreasing when g prime of x is less than 0. So we're always decreasing when the derivative is less than 0. So let's take a look. We know this hinges on the first derivative. So again, if I have my function g of x, my derivative is the derivative with respect to x of the integral from 0 to x of f of t dt. Again, fundamental theorem comes into play here, and I know the derivative is just f of x. So really, if g of x is increasing when g of x is greater than 0, it's really increasing when f of x is greater than 0. And it's going to be decreasing then when f of x is less than 0. So now using that, I know I'm increasing. We said when f of x is greater than 0. So above the x-axis is going to be from 0 to 4. And I'm going to be decreasing then when I'm below the x-axis, or from 4 to 6. Now, concavity, we're going to take a look at the second derivative here. So if g prime of x, we know is f of x, I know that g double prime of x is equal to f prime of x. So with concavity, we know that g of x is going to be concave up when g double prime of x is greater than 0. And it's going to be concave down when g double prime of x is less than 0. However, using what we saw here, I know g double prime of x is equal to f prime of x. So really what I want to know is I'm going to determine concavity by looking at when f prime of x is greater than 0, or when f prime of x is less than 0. Now, keep in mind, f prime of x less than 0 means the slope of f is negative. And f prime of x greater than 0 means I'm looking for where the slope of f is positive. So you can see a lot of this ties into when we're analyzing graphs of f and f prime to determine these same things. So now I can say that I'm going to be, let's see, that orange doesn't show up really well. I know that I'm concave up. Let's see, we said when the slope of f is positive, so from 0 to 1. And then I'm going to be concave down where the slope of f is negative, which is really, let's see here, it's 0 between 1 and 2, so from 2 to 6. So that's how we determine concavity. All right, so now we're going to do the last piece here, question 6. We're going to do the same thing, looking for increasing, decreasing, and concavity using an accumulation function. And then I think topic 4 we'll save for going over in class. So we'll just get you kind of these basic pieces, and then we'll pull it together in class. So let's go ahead. Let's do the same thing. Now we don't have a graph anymore, but we have our accumulation function. Again, g of x, where it's increasing and decreasing, we know depends on our first derivative. So g prime of x is going to be the derivative with respect to x of my integral. So I know that's going to be x squared minus 1. Oops, let me move that down. So now that we have our function here, we have to remember now we need to decide where this is positive and negative. So this is going to be back to where we were before, where we have to find the critical points, make our table, and then do an analysis to determine where g prime is positive and negative. Okay, so now we've found our derivative already. That's our first step. So now we're going to set that equal to 0. All right, we know we've got x minus 1 and x plus 1. So now we've got 2 critical points. So we've got x equals negative 1 and 1. So I'm going to go ahead and make my table. Here's g prime. I've got negative infinity, negative 1, 1, and infinity. So now let's go ahead and test some points. So if I plug in negative 2, this is going to give me a negative times a negative, so I'm going to be positive over this interval. If I plug in 0, I've got a negative times a positive, which makes me negative. And then if I plug in a positive 2 here, both of my factors are positive, so I become positive here. And so now we just use our table, this is more like what we're used to doing, to find our intervals. So I'm going to be increasing from negative infinity to negative 1, and 1 to infinity, and decreasing from negative 1 to 1. Okay, now concavity, we're going to take our second derivative. Well, our first derivative was x squared minus 1, so I know my second derivative is equal to 2x, and I'm going to find where that's equal to 0. So obviously that's at x equals 0. Now I've got my table for g double prime. Got negative infinity, and in the middle is 0. And again, I'm going to test points to determine the sign. So if I plug in a negative 2, I get negative value. Plug in a positive 2, I get a positive value. So now I know I am concave up from 0 to infinity, and concave down from negative infinity to 0. Okay, so really we have the basics now to work through topic number 4. I think that's enough for today, just getting familiar with making sure we can find function values, find derivative values, and then determine where we're increasing and decreasing. We'll do topic 4 in class tomorrow before we get into some more practice.